Our second speaker for the night is AMAN ARORA. He works for CoreLogic Australia, implementing automatic valuation models. So he's probably going to disclose today when is the best moment to buy a property in Sydney. He promised that, so I will be very disappointed if that doesn't happen. And he's going to do that as part of a wider talk on transfer learning. He's going to explain why this mechanism implemented in deep learning has become so popular, and I think Jeremy Howard is coming into the story. So please welcome Aman. Thank you.
Yeah, now is a good time to buy a property. Everybody run. Okay. Can everyone hear me okay?
What?
Can everyone hear me okay? Yeah. I really wouldn't know what to do if someone said no at this stage. So bear with me. Alrighty. Why transfer learning? I guess I'll get straight into the talk. And when I was coming here for the meetup, I was trying to decide, while I was preparing what the slides should be, while I was thinking what the topic should be, and I got to know I'm going to be presenting at Data Science Sydney, I was trying to come up with a topic that would be helpful to everyone that's present here today. And the reason I've picked up transfer learning is manifold. The reason I've picked up transfer learning is, I don't know, just out of curiosity, how many of us have heard the word transfer learning before? Okay, fair few, and yeah, so fair few still haven't heard the word transfer learning. Does this still sort of intuitively tell you something that it's going to be about transfer of learning? That it's going to be something about that someone will know something and they'll transfer that knowledge. So there's still that intuition, so it doesn't assume any amount of data science knowledge whatsoever. And that was one of the reasons why I picked up transfer learning, because it's something that's machine learning, and it's usually considered a black box. Machine learning is usually looked up as a black box, that it's something I don't understand, or but transfer learning definitely is top there, that it will make sense intuitively as well. It has business applications use case. So in today's world, if we look at image classification, if we look at text classification, so all the topic modeling, if you're a business or if you're a startup and you get support tickets and you want to classify them into what support tickets they are, you want to categorize those support tickets, then transfer learning is going to help you. If you want to build like a model that predicts the next sentences in a word, transfer learning is going to help you. If you want to build an image classifier, maybe that's genomes, cancer detection, or maybe it's even like a property image detection, or if it's a house or if it's a unit, transfer learning is going to help you. So it's got all these use cases in images as well as text, and it's really become the norm today in terms of images and text. So without telling you what transfer learning is, let me first tell you it has got a lot of use case. It's very fast and easy to implement, and we'll eventually get into this in the coming slides. It works. Transfer learning has led to a state of arts in so many research papers today that every research paper that you pick up, if you're reading research papers, if you pick it up in images and NLP, transfer learning is the thing that's going to be top there. It's like the XG boost at Kaggle. If you look at Kaggle competitions, you see all the winning posts. You see XG boost is winning this, XG boost is winning that. Then that's the case for transfer learning and deep learning. Doesn't have massive data needs. We'll get into that as well. And it's the next big thing. That's not me saying it. That's Andrew Ng saying it at NIPS 2016. So at NIPS 2016, that's a machine learning conference that happens annually. And he said in 2016 that transfer learning is going to be the next big thing for commercial success after supervised learning. And he predicted that in 2016. Supervised learning, for any of you that don't know what supervised learning is, it basically means labeled data. So you have something you want to predict, and you know what you're going to predict, and you have an answer for it. But transfer learning, he said, is going to be the next big thing after supervised learning. And he predicted this chart. And for someone like me who looks up to Andrew Ng, who really appreciates his foresight, that 3 years after, that's exactly what's happened. Transfer learning has come into deep learning, and it has really picked up. So let's finally get into the talk of demystifying transfer learning. Today I'm going to be talking about what transfer learning is. I'm going to be talking about sort of intuitively it's going to make sense what transfer learning means, how it works, and a little bit technical, but it doesn't assume that you have any prior knowledge of deep learning or transfer learning. So what is transfer learning? Unfortunately, Eugene isn't here today, but I have a story about him. So he's traveling in Shanghai, but that's what I've been told. Sorry?
I can still explain it even if he's not here.
Yeah, I'm going to. It's part of the presentation.
He will see it.
So there was my journey as a data scientist started at this very meetup a while ago, and like many of us, I went up to Eugene and I asked him. I said, Eugene, I want to pick up data science, and how do I start? What's the one thing that I start with that I can be good at data science? And he said, go back, study statistics, come back and pick up machine learning. So he said, study statistics first. And let's take a step back now, and let's try and understand what he was trying to say. He said, study statistics first. So you build that basic base of knowledge of statistics, right? Before you get into machine learning, you build that base layer of statistics. Then you build up on top of it, and you start learning machine learning. And that's exactly what transfer learning is. He was asking me to do transfer learning. He asked me to start with statistics, keep the basics. So if you think of studies as layers, so let's say statistics is the bottom layer, and the base formula and the very the things that we don't really that frighten me, those formulas are the second layer, and then there's machine learning. But if I just keep the basic knowledge and I come into machine learning and I start picking up machine learning, then it's going to be a lot easier for me to pick up machine learning because I have some prior knowledge. I don't enter the field not knowing anything. And to me, that's transfer learning. And in fact, the CEO of DeepMind, Demystify, he's, if any of us have played Theme Park, a multi-million-dollar game, he designed it when he was 17. He now works for Google. And he said, transfer learning is the key to general intelligence. So he said, start with a general knowledge of something, and then that's your general intelligence. So you get that idea, that base of statistics, and then build on top of it and start getting into machine learning. So he said the transfer learning is going to be this idea of general intelligence. Sorry. So, and for some reason, when I was looking for slides to put up, and I was looking up at NVIDIA, they have a blog post, and it's got pictures of 3 horses, which to me doesn't make sense. And it says, transfer learning has to be something with the Wild West, so I don't know why that picture is there. That is not transfer learning. Alright, agenda for today. Today, we'll get the building blocks in place. First, we'll start with, before we really get into what transfer learning is, we'll start with the building blocks. We'll start with having a look at neural networks. What does it mean to say that I'm doing deep learning? What does it mean? What do neural networks mean? And then we'll have to start looking at transfer learning as an example of ImageNet, that's in images. So we'll have a look at an example of transfer learning in images. Then we'll sort of make an analogy of comparing it with the backbone and head comparison, and we'll see how transfer learning can be compared to a backbone and head. And we'll get into the next example, which is text. And finally, we'll have a look at a code snippet, and we'll see what, this is something that you can go back and implement in your own business, or for your own studies if you're a student, or for your academic projects. And we'll just have a look at the code snippet, and we'll have a look at what the final outcome could be. So let's get into it. From this point onwards, we'll start digging a bit more into transfer learning with each slide. And the first thing that comes up to transfer learning today with images is ImageNet. What is ImageNet? Fei Li, she's another person at Google. She said there was this whole idea in 2013 to come up with an algorithm that's able to work with every bit of data. But she said, it's going to be very hard to come up with an algorithm that's going to work with all bits of data. Why not do I come up with a data set that's got a bit of everything? And I train my model on it, and that way the model knows a little about everything. And then I can use that model, the knowledge that it has, and I can build up on it, and I can start working on a specific problem. So that was in 2013, and she built up this idea of ImageNet that's got about 1.2 million images of pretty much everything that you see around you. So common objects, like chairs, even pets, or could be anything, like houses, or so literally the common objects that we see day to day. She built up that data set, and today it's used as the starting point for pretty much every model in images. Okay. And when she started, the accuracy started with about 71.8. And in 7 years' time, it really grew up from a 71.8 to 97.3% accuracy in predicting images. So today we see cats and dogs classifier at a 99.9% accuracy. Something that used to take hours, something that used to be so difficult before is today now a problem that's not even worth teaching in academic literature, because it's so easy now within 7 years with this idea of transfer learning. And people said, if I can do transfer learning in images, I must be able to do it in text. There must be a way that I pick up transfer learning, I maybe train it on a general text corpus, on a general text data set, and I start to do my specific problem. So that's the theme of this talk, is where Jeremy Howard, and Sebastian Ruder, they came up with this idea of building a common data set for text and building on top of it and learning to apply transfer learning to a textual problem. And that could be something that we do, something like a sentimental analysis. So it's something that classifies text. It could be something that says if the text is negative or positive, but it doesn't have to be just that. It could be a topic classification. It could be something that says this text or this paragraph of text belongs to the topic architecture. This paragraph of text belongs to a topic history. So it doesn't really have to be a sentimental analysis sort of thing, but it could be a topic modeling or a question labeling or a support ticket labeling. And that's the idea of applying transfer learning in text, and that's sort of the business use case. So neural network at a glance, I think the picture at the bottom is something that if I search neural network, it always comes up on my Google search for some reason, and it's nothing to be frightened of. That's not a neural network in my eyes. If you think of, let's say it's a repeated sort of actions of a multiplication, addition, and removing the negatives. And that's it. If you repeat that action 100 times, you have a deep neural network. So the neural network, the reason why a neural network is, when I said a multiplication, an addition, and a ReLU, that actually means, so if I have a look at this, I've got a set of multiplications. That's one step in the neural network. I've got a set of additions. That's the second step in the neural network. And I've got something that just takes the maximum, so something that just cuts away the negatives and keeps a zero instead, or if it's a positive value, it keeps the positive value. And that's it. And you repeat that 100 times, you get a deep neural network. And this is something that's just means for that. So you've got that one layer that does multiplication, addition, remove the negatives. If you do it 100 times, you have a deep neural network. And this architecture that Chloe was talking about is something that can do image classification. This is something that can do text classification. This is something that can build a language model, which means it can predict the next words in a sentence. So before we learn about transfer learning in text, let's first understand what transfer learning means. What we see that a deep neural network has layers, but let's start and visualize what does it mean to have layers, and what does each layer sort of learns in in a deep neural network. And we'll have a look at as an example of images. So we're going back to ImageNet, which was about classifying images of common objects, whether it's a chair, or it's a ball, or it's a bat, or anything like that. And we fit and this is a research paper that was released some time ago. And what they did was they fit a neural network, which is a deep neural network, which is a repetitive layers. You fit that on ImageNet data, and you're trying to predict what image category it is. And you fit that image, and what they try to do is they try to visualize what each of the layers are going to be. So let's have a look into what each layers actually sort of learn in that deep neural network. Okay, so we see the first layer. This is the one that's the very bottom layer, and this is the sort of thing going back to when I said keep the basics of the statistics. So this is the very basic foundation of the first layer. And we see what this learns is something that finds the edges. It's something that groups pixels together. It groups green pixels together. It's something that knows how the yellow pixels are, or it's something that knows the diagonal in the other side. So this is the very first layer of a deep neural network that looks like this. And I'm trying to visualize this layer here, and this is what it learns if you train it on an ImageNet. Going forward, in a layer 2, the second layer builds on top of what it learned from the first layer, because the data is going to be passed from the first layer to the second layer. So the second layer builds on top, then the third layer builds on top of the second layer, and so on. So the second layer starts to learn something that the first layer was just picking up lines, but the second layer starts to pick up 2 lines, so it knows how to pick up a corner. And we see that here. Or it knows how to pick up these parallel lines here, or it knows how to pick up these circles here. So that's the second layer. As you can imagine, the third layer will build on top of the second layer, and it will start to learn repetitive patterns. It will start to recognize wheels. It will start to recognize, so these are all sort of building on top of the second layer where it learned to do 2 lines, but then now it can do multiple lines. It can learn what a wheel is, or something around those lines, and it can sort of pick up furs in a pet's data set. And then you can imagine by the time we get to layer 4 or 5, the things that it starts to pick up are common other objects that it's starting to get there to the point where it can categorize pets, or it can categorize images. So somewhere in layer 4, it can pick up dog faces, or it can pick up bird legs. And by the time we get to layer 5, it can classify between dog breeds, not only pick up dog faces, but classify those dog breeds into what the breed exactly is, or classify if the wheel is bicycle and something like that. So you see, by the time we get those 100 layers of this ImageNet, which is a deep neural network, these are just the first 5 layers. By the time we usually have about 34 or 50 deep layers such as this one. And by the time we get to a 50th layer, it is something, if it's an image problem, it is something that can predict if the person, just by looking at a cancer image, it can predict if the person has cancer or not, or it's something that can predict if it's a house or a unit or not, or it can do object detection. It can look into the object and can say, this is a sofa set in the living room. So you can see how building on top of each other, it gets to a point where the neural network starts to get really smart. And it starts to learn, and it starts to become this classifier that suits our problem. But then, let's take a step back. Let's take another step back, and let's really think. If I want to do any sort of image classification, and if I want to classify whether it's a dog or a cat, and that's my dog cat classifier. If I want to classify if it's a bat or a ball, and that's my bat ball classifier, or if I want to classify who the cricketer is and the cricketer faces. The first 2 or 3 layers are going to remain exactly the same. The edges are still going to be edges. The group of pixels are still going to be the green group of pixels. And the borders are still going to be borders. The only thing that we need to do is say, keep those three layers of knowledge, keep that knowledge that you learned by doing something on a different problem, keep that knowledge, and I'm going to retrain. I'm going to teach those 2 layers at the very top to do something else. So that's transfer learning. That's the idea of transfer learning, is that you keep the basic knowledge, you keep the idea of what a corner is, you keep the idea of what green pixels mean, you keep the idea of what a window means, or something around those lines, and then you just train the final layers. You ask the model to learn on those final layers on the problem or the thing that you want to do in your business. And that's just an example using images. So if we think of that layered network as a backbone and a head, and that's the analogy that I was talking about during the agenda, is that if we think of each neural network as a backbone and a head, and that backbone means that early layers of knowledge, that base knowledge of what a corner is or what the group of pixels are, and I think of the head as the specific problem that I want to do in the image case, which could be coming from a property company. It could be whether to determine if it's a house or a unit, or if you want to do a classify to determine if it's what cricketer it is, or if it's a football or a cricket, or any sort of problem statement that you want to work with, and that's the head. And if we're able to think of classification, or if we sort of think of a problem into this idea, then we can do transfer learning. So that's again sort of just saying that if we think of any neural network as a backbone and a head, then we can do transfer learning if we just change the head. So the theme of today's talk was to introduce ULMFiT, and I can't stress this enough, and I can't give enough credits to Jeremy Howard, Sebastian and fast.ai, because pretty much all of today's talk comes from what I've been able to, it comes from the best bits and pieces of fast.ai and what they've done in the work. They're doing groundbreaking research, and they're trying to bring deep learning to everyone, to make it so affordable and to make it so easy to understand. And this is the research paper that they did, was about ULMFiT, where they applied this idea of transfer learning, of having a backbone and of having a head, to text. And this is how they did it. So they built a language model. Now, we probably don't know what a language model is, and that's a language model. If we've used Google, and I start to type something in the Google email, I go, how are the things? And the Google predicts what the next words are, and that's a language model. So what Jeremy Howard and Sebastian Ruder thought of, and they said, let's try and do what the ImageNet people did. Let's replicate that idea and do it in text. So what they did was they trained a language model on a Wikipedia dataset. And as you can imagine, Wikipedia has every sort of text. Wikipedia is where you get to know little about everything. So it's sort of like that ImageNet dataset that's got about 1.2 million images of everything. So the model at this stage will know a little bit about everything. It will know a little bit about news articles, it will know a little bit about architecture, it will know a little bit about history, and that's your starting point. And then they said, you keep that language model, you keep those early layers, that whatever you learned about text, you keep those early layers, and you apply that to your problem. So coming from a property company, if I've got a listing on realestate.com and it says this property does this, or this property is close proximity, and I've got all that text, and if I start then training this language model on a property data, then not only does it know English, at this stage it knows a lot about the property domain as well. And if you apply to, say, the second point at your support tickets or a customer service company, and then at that point it will not only know English, because in Wikipedia it learns how English is spoken. It sort of learns a little bit about everything. But then when you apply it to your domain, to your specific domain, it picks up that domain knowledge as well. So that's my second step. I start with learning basic English. Then I teach the model to learn something about your domain. And the third step is the classifier. This is the custom head that sits on top. So whether you want to do topic modeling, or you want to do sentimental analysis, or you want to do just a score rating, and that's the classifier that comes in the end in a particular domain. So that's the idea of ULMFiT. It was at some stage referred to as the ImageNet moment. Why? Because it's that parallel. It just like ImageNet in 7 years went from 71.8% accuracy to about 97.3% accuracy. In text, the same thing happened. They broke all records of state of art that existed. If it's an IMDb movie review data set, the error percentage came down from a 5.9 to 4.6, which is about 20% reduction in error rate. Just by this idea of transfer learning, that you don't start afresh, you don't start looking into the domain without not knowing anything about the domain. You start with some little knowledge. And this time they started the language model that it knows English and it knows something about the particular domain. And that's when you start doing the problem statement, which could be the classification. And they applied it to a whole bunch of data sets, which is IMDb or a Trek 6. A Trek 6 is a sort of like a topic modeling data set as well. And the AG is the news corpus, and Dpedia is again a sort of like a classification sort of problem. And the one thing that you can see in here, and Yelp is again the movie sort of the reviews website that's the common data set that's frequently used in academics. So the one thing that we could see is that they reduced the error rate that existed, and this approach was introduced last year. So last year, they broke all state-of-art records, and it became the new norm. Now there have been more research papers in terms of BERT or just unsupervised or semi-supervised learning, but they build on the same idea of transfer learning in text. So the thing about transfer learning, at the start I said, it's not necessary that you need a lot of data. Why? Because the model starts with some knowledge, it doesn't really need a lot of data to do what it has to do had it started fresh. So had it started not knowing anything about the domain, it would have to do a lot more than when it already knows something about the domain. So it already doesn't start randomly, but it starts with some set of weights. And we can see that the number of samples in all these data sets is varied, but it still performed and it still gave the state-of-art results. We can also see that the classification has a different number of classes in each of these data sets, but it still performed and it still gave a really good result. So that's transfer learning idea in images and text. And applying to both domains, it has given great results. So finally, we'll just have a look at a code snippet, and it's everything that's been discussed in today's talk is a part of tutorial. It's free for everyone, so you can go back and do that course, and it's fast.ai, and you can go back and do the course. And I did the course, and I tried to replicate the results of that research paper using their library. And I saw that by running it on a Yelp sort of sentimental analysis, I saw that I got an accuracy of 97.5% classification in text. So, and that's amazing, because in the research paper, they said you should be expecting about an error percentage of 2.16, which is about 98.4% accuracy. And by replicating myself, I was able to get about 97.5% accuracy on the same data set by running the same code. Of course, they put in a lot more smarts than I know about it, but doing it, I was able to get the same sort of accuracy. That's pretty good. And when I tried to play with the predictions, and because I used it as a sentimental analysis sort of problem, and when I tried to play around it, and I said I passed it to different texts that it could normally expect in a review sort of thing, and it saw. When I passed it, I really enjoyed a lunch, went with my wife and kids, and had a steak sandwich, which was delicious. It predicted a category 5, so it knew it's a positive review. And when I said these guys were dishonest and service was bad, it knew it's a negative review. So this model has not only at this stage learned how to speak English, it's not only learned how the customer service or the food industry works, but it's also picked up negative or positive sentiment, if there's any in that text. And when I was doing the language model, which is the one like Google that predicts the next words, and I tried to replicate the results, I was able to, I trained it on a Sherlock Holmes, which is the one I found on like a text file, and I trained the model to learn something about, say, Sherlock Holmes. And it's not perfect, but it said, I just passed the 2 words Sherlock Holmes, and it started to generate this text by itself from what it learned out of English and that domain knowledge, and it said who was the last man, and that he was a man of most extraordinary tribe, and it's sort of just repeating itself there at this stage. But then when I passed it, and this was something that I was doing about 5 months ago. Recently when I was doing it for the Yelp dataset, and I said this place was really, it said, and this time the model worked a lot better. It said this place was really good. First off, you're looking for high-end dining, you can count on Chef Chris. I love to give places. I love to give places, which doesn't make sense, but it's getting there. It's close. I love to give places such a great rating. Okay, so it does make sense. He's great and he's a great server. So you can see now this model is predicting text. It's predicting what the next words are going to be, and that's the power of transfer learning. So if there's any takeaways from this talk that I would say that's key takeaways, it's sort of try transfer learning, try the script, try the tutorials, and in very less time you'll be able to implement everything that I've presented in this talk for yourself. So just spend a few hours on this, and try this idea of transfer learning, and Jeremy Howard will explain it in a lot more detail to you. And hopefully it served as an introduction and some motivation to do transfer learning. So in terms of next steps and in terms of resources, well, fast.ai is definitely there, because it has helped me learn a lot more about deep learning than I knew otherwise. I've presented the research papers that are there that I talked about during the presentation, and of course some other resources. So go back, have a look if you enjoy it. Just rerun the code and you'll be able to present. You can just pass in your own text. Anything that you want to do, just pass in your own text, and you'll be able to build a language model, or you'll be able to build a classifier in, I would say, a few hours' time, just by rerunning the whole code. So thank you very much for your time. Happy to take any questions.
Does text transfer learning for text work better than images then? Because images can be so corrupted. So.
Well, what do you say? Text can't be corrupted. Because there's whole sets of symbols, or there's whole sets of, it depends on the data that you're training with. I would say it's the same for text as well.
Thanks, Aaron. Just to introduce myself, John Patrick, from a company called Health Language Analytics. We've been doing natural language processing, computational linguistics on text for, well, I've been doing it for 30 years, and my company's been doing it for the last 10 years or so. Can I just advise you to temper your enthusiasm slightly, if I may do it politely. I think there are a couple of dimensions here which you haven't reached into, which are worthy of consideration. I think the first thing is that all the examples you've shown and all the examples I've seen of successful text processing like that have been about document classification. Okay? And it's important to understand that a huge amount of natural language processing is about entity recognition within documents.
Sure.
Okay. We have had 2 major efforts in our own corporation to use neural nets, deep learning, whatever you want to call it, for entity recognition in clinical documents, and being totally unsuccessful at getting improved results against supervised learning exercises. And so I think that's something, everyone in the room needs to understand, that it's good at one level but not at another level.
Sure.
Okay? And I give you credit that you did say that your early slides showed there is a difference to it. But we have to temper our enthusiasm for this method. I think the other dimension that we found from what we did was that even though we built neural net models with documents which were then analysed with the neural net that they were built with, they were still not good as. In other words, we are using the same data. We built models and then tested them on the same data that the model was built on. We still couldn't get better results than supervised learning. Now, I'm frustrated with my staff in not being able to get better results from neural nets than what we are. Okay? But my staff have been unable to show that something improved for the entity recognition task, okay, as distinct from the document classification task. We also found that when we use logistical regression for document recognition, document identification task, even that was better than what we could do with neural nets. Okay? And we don't understand why. Okay? So I'm happy to say there's more room for us to learn on that. But I do find your enthusiasm a little overwhelming, as much as I appreciate that you've discovered something that's valuable to you and you use it in your work. Thank you.
If I may, I suppose in the whole talk, thank you very much for that opinion, and I really appreciate you giving us a different side of the coin, because it's really important to understand both sides of the coin. So thank you very much for that. I suppose I just want to say, when you say logistic regression is a better model, perhaps the thing that it's doing is that it's picking up those specific words. And perhaps the thing that you might have done, I'm only assuming and I haven't seen the data set, is perhaps the thing that you might have done is maybe build the traditional sort of that picks up two words or one word, and it starts to then, or maybe a trigram or a bigram, and it starts to then, on top of that, it starts to see which words come together. And then on top of that, it starts to build up. It starts to pick those specific words in those documents. And then that's perhaps the reason why logistic regression was working better. I'm only assuming. The transfer learning bit in text is literally not about entity recognition, because it's different. The whole theme of this talk has been about classification. And in doing classification, it's a very different problem from an entity. It's a very different problem from an entity recognition in my eyes, because in images that would be something like object detection, but in text, entity pickup would definitely work a lot better if you're doing bigram. So I completely take your point with 100% respect, and the only thing I feel is perhaps the data that we've been working with, or the problem statements, or the domain that we've been working with, and the kind of problems that we've been trying to solve are very different. Thank you.
Hi. I was just wondering, you went through... Sorry. Hi. You went through your own examples of like predicting reviews, whether they were 5-star or 1-star.
Yep.
Now, I would imagine that the ones in between, like the 2, 3, 4 stars, would be a bit harder to classify. So did you yourself do any of that?
I haven't, but these guys who released this research paper on this exact talk did it for themselves by doing the library, and I've personally done more than classification that involves more than 2 classes. It did work for me, not on the exact specific problem, but these guys, when they did it, they found good results.
Yeah, I just imagine that like this sort of classification would be fairly close together, especially for the 2, 3, 4 stars, you know.
Yeah, it would be very difficult. It's definitely a big, more difficult problem than very good or very bad. So
yeah,
it's
exactly.
definitely it's definitely a bigger problem.
All right, thank you.
No worries.
Hi, thanks. I wanted to just ask about how you get the initial layers trained, because it seems convenient if you can just take a pre-trained layer or several of them and supplant them. But even those training processes, they're still supervised learning, right? So they must have had some kind of labeling on the data that was done. So I was just wondering how you go about choosing the suitable label to start forming out crucial structures in your general data set, like edges or sentence structure or phrases, etc. I mean, I could see perhaps if you've got ImageNet just finding the first few objects that jump out at you as being present might be a sort of obvious label set, but if you're choosing, say, a corpus of text like Wikipedia, do you do a kind of a continuous sort of what's the next word kind of labeling, or how do you go about labeling something like that to get a generic good kind of first few layers trained for a general problem that might be quite different in terms of the specific subject matter label you want to choose later?
That's a really good question. So I guess with Wikipedia, it's not really doing classification. What it's doing is it's predicting the next word. So at this stage, what it's doing in an NLP, I'm assuming you've used embeddings. So what it's doing is it's building embeddings for every word. So in a simple way, if I would say, it's building some weights that get assigned to each word. So at this stage, it's not really doing any classification. It's just building context, if you may. So with Wikipedia, when we're building language models, we don't do any classification. We just predict the next word. And then by the time it's learned that context, that's when we get into classification. So I'm happy to chat a lot more about this afterwards, but it's essentially to just say it succinctly, it's building embeddings, it's training those weights, those embedding weights, and then it's doing classification in the end.
Hi, first thanks for the talk. And
You're very welcome.
did you have to do any pre-processing? And also, what was the actual model architecture, or was it automatically generated by the fast AI?
So in terms of pre-processing, it's not something that I've done, but what fast AI does is for pre-processing they don't really have to go in and clean the data set, but they just say if the word doesn't appear more than 2 or 3 times, they generally say 2 times. If it doesn't appear more than 2 times, I'm going to take it away. So in that sense, it will take away all the incorrect, misspelled words. And they also put a cap on the total number of words to be 60,000. So that's something that they do very smartly about, and they just keep the 60,000 words. So that's the pre-processing bit that comes in.
And the model architecture?
Yeah. So the model architecture in itself is an AWD LSTM. What that basically means, is, sorry, I don't have a slide, so I'm just trying to put it here. What that basically means is, I'm assuming you know RNNs, and so in an RNN, when the 2 words come to you, first the word comes in, then it trains it, then the second word comes in, and it trains it, and then the third word comes in. In an LSTM or an AWD LSTM, what it does is, there's a neural net to decide how much weight do you give to which word. So it sort of keeps to context, and it keeps it context for longer. So that's the architecture, it's LSTM.
Thank you.
No worries.
So you've done a very interesting demonstration of how we can use an already trained network to save time learning a more complicated task once we've trained on the simpler one. Could you get a better overall result with a complicated task if you deliberately trained smaller networks on the simpler tasks first? It's a bit like when we teach children things at school, we teach them the really basic stuff first. And when we've got that, we then build on the next difficult part and then time. So, I mean, you could apply that approach, you could use this to do that here. Would you get a better result, do you think, with a more advanced task?
That's the intuition of transfer learning. So that transfer learning in itself is, you start with simpler things and then you build on top. So when I first picked up this library and when I first started learning about a year ago, I got into a cancer detection competition at Kaggle. It's called histopathologic cancer detection, and that's a very complex problem in itself, because you have those X-ray images and you're trying to still predict if it has cancer or not, so it's trying to find those cancer cells and stuff like that. So that's a very complex problem. When I started doing it just with that, it didn't work so well. But when I started with ImageNet, that starts with a ball or a bat. But I suppose with this sort of problem, you want to go further back into the layers. You just don't want to retrain the final layers. You want to go back to all the way when it starts to find those windows. So that's like layer 2 or 3. So you want to go further back. So the more complicated problem that it gets, you still want to start with the simpler things, but you want to go a little more backwards and retrain the model, if that makes sense. Because if you go further back, then the more basic you get in terms of, the more granular you get in the model. So because it's going from detecting bat and ball to a cancer detection, you want to go all the way back into the model and start retraining those things.
Right, so you train on the simpler things and then you then allow it to retrain itself on the simpler things once you...
Yep, so you say you've got about 34 layers and you train on the simpler things, you go all the way back to, instead of 5, you go all the way back to 10 or 15. So you still keep that early knowledge. And that really helps. It still helps.
Question here.
Hi. Thanks for the talk. So you're emphasizing examples where you're essentially switching the head and retaining the low layers.
Yep.
But sort of naively, it feels like the opposite would be maybe more promising and helpful, in the sense that often you'll want to perform a task like translation or taking in images of completely different kinds or cross-modality sort of inputs. And the higher layers, the more abstract semantic layers, take longer to train. So it would be sort of very interesting if you could actually swap the sort of abstract layers and essentially retrain the sort of lower input layers predominantly. Have you come across any examples where you do that instead of the opposite?
No. I suppose when you say train the abstract layers, do you mean the earlier layers? So if you've got
the high layers where you have
so if you've got a model starting with layer 1 at the bottom and layer 5 at the top, when you say the earlier layers, do you mean the layers 1, 2, 3 or the layers 4 and 5?
I mean discarding the earlier layers as in layers 1, 2, 3.
Yep.
And retaining the sort of abstract layers that sort of encode the relationship between conceptual or semantic sort of characteristics of your data set, which might be shared across sort of language and images and various other things.
So with text, it's a different model. With images, if you've got layers 1, 2, and 3, those layers are pixel level layers. They find the edges, they find the colors. So you never want to change those layers. In my experience from when I've worked on this library, you never want to change those layers. And even the folks that build this library and all the forums, that's what they say, that you never want to change those layers in images. In text, I particularly haven't worked with translation, so I don't think I'll be able to answer that. But with classification, I never had to change the early embeddings from the problems that I've seen.
Okay, we're going to do the last one. The very last one.
Hi, thank you for the talk. My level of data science is very basic, so we'll ask a broader question. What do you think is a more disruptive business application of what you showed us? Because it, of course, looks very interesting, but I fail to understand kind of
Are you saying
strong business application.
Are you saying predicting the next words of a Sherlock Holmes novel is not as disruptive?
No, it's very technically. I'm impressed, but I like in our daily life, how can really affect that?
So in daily life, people have used this to build their own WhatsApp images classifiers. So something like this has been used, and these are all daily projects that I've learned from the forums of the fast.ai library that you can have a look at as well. If you go into forums and you see a share your work column, people have used this as in terms of the image classifiers, they've used this to do something like a Panama bus classifier, which is their sort of thing, or it's a hot dog or not, or something like WhatsApp images classifier, which to me I found really practical. So what they've done is, because you get all these spam and all these images in WhatsApp and then people forward you all these things, they've really, they've built models that start to recognize their family and those images, so you keep those images important. And that's sort of the, really it's up to you where you take it. But in terms of and that's in terms of a personal. In terms of business, the use cases that I've seen in text are around classifying support tickets or classifying customer problems or classifying questions, or if you're a law firm and you have all these texts of data you want to classify that And to the law and the government, this is something that, because they don't want to go into that billions of text, they just want to classify it. And those are the use cases that I've seen with text.
Just to add to that, I've also seen it used to like predict fake reviews on review websites as well.
Absolutely.
Like
and fraud or not, or if it's if it has toxic intent in the sentiment, or if it's something that's using rude language, then you want to monitor that. And that's one of the use cases as well. Thank you for that.
Thank you very much for the talk.
Thank you.
And now we have a couple of very special announcements, so please stay. So pay attention.
Thank you. Hi, I'm Matthew Clark. I do research in slavery. I look at the prevalence of slavery, the causes of slavery, and the eradication of slavery. And there's a lot of data involved there, and I've got a problem, and I would like your help. So, estimating the prevalence of slavery is quite a tricky business. And it's very difficult to know what the real trend has been over the last, say, 20 years. But it seems like it's getting worse. The most respected analysis of the prevalence of slavery comes from a research group in Perth, and they produce each year a global slavery index. And it's a lengthy document that gives a measure for each country in the world about the prevalence of slavery in that country. And they've also recently introduced what they call a vulnerability model, which does a factor analysis in order to produce a score for each country based on how vulnerable that country is to the exploitation of people in slavery-like situations. Now, my background's in BI. I've done data analysis work for 30 years in academic context and in commercial context and in not-for-profits and in software development. But the kind of analysis that they do in the Global Slavery Index is a bit beyond my depth of understanding. And I think there's a couple of problems with the way they've gone about it, but that's my suspicion. And I am hoping that some of you guys might have a deeper knowledge than me and might have some interest in justice and social good and might come and talk to me later so that we can work together to perhaps provide an independent analysis of the Global Slavery Index's approach and maybe suggest to them some improvements to it. So if you're interested, I'll hang around afterwards. You can come and talk to me. I'd love your help. Thanks for that.
Thank you. And the other announcements is like about our video sponsoring. So we have today Prescient, Eugene's training company, sponsoring the video, but that's not ideal. So Eugene is already putting a lot of effort in the community. So we would like some other company to help us sponsoring the video and the great work that Troy and the team is doing. It's not a great investment for a company. I think it adds a lot of value to the community. People who cannot attend can see the meetups later. The speakers can show the presentation that they have done externally, and it's also valuable for them. So I think the advantages are clear. So I would like to ask everybody to check in their company if there is the opportunity to sponsor this task. It's only like less than $400 per event. So for a company, that's not much. And I know it's a bit presumptuous to say that, but please do that for me, if you don't mind. Thank you very much.